Well, we're back, and we are on section P5, normal distribution. This could possibly be one of my favorite sections. Yes, that's the math geek in me coming out right there. But I do like this part because we really start to get into calculating and finding some area and some normal curves and some endpoints. I like this. So we're going to look at these major topics here. We're going to look at the density curve, the normal distribution of that density curve, finding normal probabilities through technology, finding endpoints through technology, and standardizing the normal curve. So you're going to want to have your calculator ready for sure. And we'll do a little bit inside of StatKey at the same time. So the normal distribution has a symmetrical bell-shaped density curve. And that's what we mean when we say the normal distribution. It's symmetric, it's bell-shaped, and the density part of it refers to the area underneath of the curve. The area, or what's under here, is 100%. The entire curve, not any specific distance from the center, but 100% of the area, or 1.0 of the values are underneath of that curve. And we're talking the curve infinitely left and infinitely right. Two features that distinguish one normal density curve from another. Okay, so we have to be able to look at two curves and say, okay, the data from this one means something different from the data from another. Well, one thing is the mean, or the center, mu. Where is the center of that curve? Because a curve, although symmetric, can be shifted left and shifted right. And the mean is what will do that shifting. The second thing is the standard deviation, the thing that controls the spread, how wide that spread is. I mean, in today's day and age, right now, I'm talking to you via distance education for a reason, because we're trying to flatten the curve. We're trying to spread the standard deviation from the center of a particular item. I think that'll be the topic of the yearly word, is flattening the curve. The notation that we'll utilize is x, or the normal distribution, of some value mu at some center, comma, with some standard deviation. For example, any case is normally distributed with a 3 center and a 0.6 standard deviation. We need to learn to read them as they're giving to us. Value here indicates normally distributed. Value here indicates the center, or where the curve is going to be hovering around. And the value here is the spread, the standard deviation. So as we look at a curve and we look at it on a standard deviation, or on a normalcy, we find our center, mu. So the curve is always symmetric about the mu value. The standard deviation to the right, one standard deviation to the right, is mu plus one standard deviation. A standard deviation to the left is mu minus one standard deviation. And as we continue another standard deviation to the right and to the left, we get into that area we've talked about, that 95% area, plus or minus 2 standard deviations. Now, it continues past 2 standard deviations, 3 and 4 and 5. The number of standard deviations are not limited to the left or to the right, just the decrease in the probability that it will happen because you're so far away from the center of the data. This is our normally distributed curve and the density underneath of it. It says the density curve is a theoretical model to describe the variable's distribution. Okay, so you can think about that density curve as an idealized histogram. So we take a histogram and we take data and we pile up inside of that data and we look for the area under that curve. Well, if you look at I'll show you a picture in a second. The proportion of the population in any one of the intervals of the areas, the area over that interval. Okay, well, that's hard to understand in words, but easy to understand in a picture. This is a histogram. And when we look at a histogram, we have intervals. The left side of a bar and the right side of a bar is an interval. And in that interval, it contains an area within. And when we talk about normalizing a curve, or the density under a curve, we're actually curving across a histogram to find the area within inside of an interval. Okay, so an interval just means a section or between two endpoints, and that area between two endpoints gives us a density. How dense is the data under the curve? For instance, we might ask what proportion of GPAs are between 2.8 and 3.2. This is an interval. And in that interval, the proportion is looking for an area. I'm going to add some words for you here. Whoops, I kind of missed the word proportion there. An area. Okay? Could come to us in a percent, could come to us in a decimal. GPAs between these two numbers. This is our interval. Also, these numbers, 2.8 and 3.2, these are our endpoints. These are what define the interval. Now, how would you calculate that? Okay, well, we're going to need some advanced calculus in order to get that done. And even with that advanced calculus formula you see sliding up on that screen right there, and don't panic because we're not using that formula, a good mathematician would have a very difficult time defining that area and finding the values of it. But luckily for us, we live in 2020, and we have some phenomenal technology that's available to us to calculate the area of this curve, okay, and to find endpoints of this curve. And we're going to utilize that technology today. Now, if we break this down into what we're looking for here, first of all, we can use our calculator and we can use StatKey to achieve these things. Okay, and I'll show you a little StatKey to begin, but then I will rely more heavily on the calculator because people don't walk around with StatKey. There are two ways of using StatKey and graphing calculators to find either the area or the endpoint. These are the things we're going to find. We're going to find area and we're going to find endpoint, and it's going to be your job to figure out which one. On a normal distribution, it says you need to know both of the values, how to use StatKey and a graphing calculator, but only a graphing calculator is allowed on an examination. You're really going to want to use a graphing calculator. It's going to be more leading to what you're going to do. Now, how will I know what I'm supposed to do? Am I supposed to find area? Am I supposed to find an endpoint? Well, here are the questions that will be asked, and here's how they'll be phrased to you. For instance, if you see the word proportion, proportion means you should be trying to find a p-value. A p-value is an area. Okay, and I'll show you how to find that p-value. We've seen that on StatKey already. This is the area which is shaded to the extremity, to the right or to the left or in between 2 points. If you see the word area, same thing. If you see the word probability, same thing. All of these words point to p-value, which is area. If you see the words cutoff, endpoint, or z, you see any of those words, maybe even what score, then you're looking for something on the x-axis or the z-axis. And we'll discuss the difference between the x and the z pretty soon. You're looking for an end point. End point. There's only two things to calculate here, guys. Endpoints and area. When you're picking a tail, we've had this discussion a couple of times already. Above means greater. Below means less. And two tail means between. Okay? So let's talk about using StatKey. So first of all, we'll use the theoretical normal distribution. And I'll show you that in a minute. We'll do a demonstration. And we are going to calculate based on a couple of things. And here will be what the screen looks like. One, we'll be able to adjust the mu and the standard deviation values. We'll edit the parameters. Two, we'll be able to pick the tail, left, right, middle, just like we always have. Three, we'll be able to establish endpoints. These endpoints could be z points. They could be scores. These are endpoints of an interval. And we'll be able to find the probability or the p-score or the area. All those things mean the same words. I'm trying to use all the words that are associated with these different values. So for instance, I want to jump to StatKey for you. Sorry, I had to think what I was doing there for a second. So I'm going to jump onto StatKey. And here we go. So I'm going to go down here to theoretical distributions. Right now, you want to be in normal. Same screen comes up that was just a second ago. Now, there's not going to be data to pick over here like there has been before, but there's going to be a mu and a standard deviation. So in our next one that we're about to go back to, I'm going to go back to, it says that we have a mu value of 580. We'll see that in a second. And we have a standard deviation of 70. Edit, say OK. So I have those centers. Now I got to pick a tail or I'm not going to see anything going on here. And this one, I'm going to pick a right tail. You can see that I now get a p-score, which is associated with an endpoint. If I change the endpoint, the p-score changes. If I change the p-score, then the endpoint changes. Remember, the p-score is the amount of red area on the right-hand side. There's about 2.5% of this area consumed over here. If I make this area 5%, then the p-score has to scoot, or excuse me, the endpoint has to scoot over to accommodate twice as much area. If I make it a left tail instead of a right tail, then it just simply moves its area to the side. If I make it a two-tail, well, then there's a two-tail. I can split those values, and notice I'm ob-length here. I have 5% on the right and 2.5% on the left, and I'm able to do that because I'm still dealing with a middle of 580, and I know it's 580 because I put in 580. When we talk about a p-score, red area. When we talk about an endpoint, numbers at the bottom of the x-axis. Let me jump ahead. This is the same slide we were just at just a second ago. Sketching and shading. So let's talk sketch and shade. If we have a verbal SAT, which is normally distributed on a 580 mu with a 70 distribution, that's the first good thing that you can do for yourself is learn how to read that notation. What proportion of application SAT scores are above 700? Okay, so right away we're talking about a right tail test. I know it's a right tail because I see the words that talk about above 700. So first of all, I would have to make a normal distribution curve. I would want my middle at 580. I would want to have my distribution at 70. So you can see on the bottom axis, we're counting by 70, 70, 70, up and down. And then I'm going to want to find a score of 700 and above. So it's 700. I'm going to put in some distribution. I just popped up a second one here. Sorry. So 580, I find approximately 700. 700 is about here. That's my 700 score. And I'm above a 700. And if I'm looking for that, it says what proportion? Okay. Well, let's go to StatKey real fast and let's go find that proportion. So we go into StatKey. Again, I have to get out of the system here. It'd be nice if I could just flop back and forth. So I'm going to reset my plot. I'm going to edit my parameters, 580 and 70, say OK. I'm going to right tail, and I want this bottom score to be 700. And I have approximately 0.43 or 4.3%. So my p-value, the score that I was looking for on the right-hand side of people or things that were above is approximately 0.043. And current slide. Redraw my curve in since I lost it. I had to lose it. 700.043. About 4.3% are scoring above a 700. Let's get to the next question. So now I have a height of n equals 68. Okay, so that means that I got to draw stuff in this time. I got a 68 for my middle. I know that my numbers go up and down by 4. 72, 76, and 64, and 60. I know I have a distribution of 4 because that's what it tells me. So I know that my numbers count by 4. It says find the height. Height is not a percent. Height is a score so that just 10% of the students are shorter. Well, if 10% of the students are shorter, I'm going to arbitrarily grow something in here. I want this area over here to be 10%. I need to know the score X that happens for that. Okay, well, got to go out. And I'm going to lose my drawing, unfortunately. But all we need is the number right now. We need the X value for this number right here. I'm going to go back to StatKey. Now I'm going to rechange things here. I have to change my parameters. So now instead of a 580, I have to have a 68. I have to have a 4 for my distribution. I want a left tail this time. I need to change this value so it's 0.1, 10%. I need to tell it only allow 10% on this left-hand side over here. And the score is approximately 62.874. Really easy to find those values and how we're calculating. Okay, so again, I made it 10% and I found the score of 62.8. If I knew the score, I would change the bottom number and I would look for the percentile. Gotta love StatKey. All right. For our next one, it says, suppose that the verbal SAT score for applications at a college follow a normal distribution with a 580, so my 580 is my middle, and a standard deviation of 70. What proportion of students have this score above 700? Well, this is what we just calculated, right? We just found this 0.43, so it helps walk you through it and show you the screenshot of it. And we found that to conclude that we have exactly the same score. We did a good job, folks. And if you were writing about it, you would write about 4.3%. And this is the second one we did, where we took the 10% and we received about 62.8 or 62.9 inches. Now let's talk about standard normal. On a standard normal, now notice what we added here is not a normal distribution, it's a standard normal distribution. A standard normal distribution indicates that we center our data on a 0, okay? We center our data on a 0, and we have always a standard deviation of 1. The way we know we're dealing with a standard normal is either we see the word standard or we see the letter Z. Z, standard normal, always uses these values. It's very easy for our brain to normalize something and say, hey, if it always is a middle of 0 and it always counts by 1, that's really easy for me to do. So this is a way for us to convert numbers such as this SAT that we just did or the height that we just did that weren't zeros and ones and convert them into what we call standard normal. Think about taking something from a fraction to a decimal or a decimal to a fraction. It's the same thing, but it looks slightly different. So here's how we calculate a standard normal, a z-score. A z-score is take the data point that you have. So this is the stat that you currently have. Maybe it's a score, maybe it's a height, maybe it's a weight. I don't know. It's something. We're going to subtract it from its current mu value, the current mu value, and we're going to divide it by the current standard deviation. This is referred to as standardizing an endpoint, okay? This is called a z-score. And the standardization of this endpoint, we will then use a 0, 1 to do the distribution. And I'm going to show you how it works, and it's very nice. So here we go. We have an example. So we have a normal distribution, okay? Not a standard normal, a normal distribution. How do I know it's normal? Because it's not centered on 0 and it doesn't count by 1. In fact, it's centered at 68 and it counts by 4. So now I need to convert this thing so that I can put this onto what we refer to as a standard normal. Well, so what I want to do here, oops, sorry, went the wrong direction. And I want the area above that 65 still. So what do I want to do? Okay, well, what I want to do is I want to convert the z-score. So I'll take the original data value. This is x, remember. The data value x came from the data position that I have, the statistic I have. The 68 was the mu value. And the 4 was the standard deviation. When I do all of that, I get a z-score of negative 0.75. Well, my brain now starts to go into circles and say, okay, if it's on a center of 0 and it counts by 1 left and 1 right, then this negative 0.75 is a little bit to the left of 0. So on a standard normal now, I can put a 0.75 negative. I can draw all the area to the right because I can count by 1 very easily. And the area under this curve, this p-value, which is area, is equal to this p-value. The two values are identical in nature to each other. They can never be different from each other. So therefore, if this area is 0.773, then this area is 0.773. We do that so that everybody can look at the middle and say, 0, I got that. 1 up, 1 down, 2 up, 2 down. Converting normals. So let's say that we have something which is normally distributed. This is normally distributed, and I want to convert it. Well, if I want to convert something to normal distribution, I use what the formula we just did. I take x, I minus mu, I divide by standard deviation. Have this formula on your formula sheet. It is on there, and I will refer to it later. If I want to come from a z-score backwards, well, a z-score backwards is just slightly different. In a z-score backwards, we'll take the mu value, we'll add it to z times the standard deviation. So we'll take that actual z number, we'll multiply it by the standard deviation of the problem, and we'll add it to mu. And the mu and the standard deviation are coming from where we're going. Okay? The mu always refers to the normal. The standard deviation always refers to the normal. But the z is part of the standard normal. So there goes some questions. So let's look here. It says, find the 25th percentile for a verbal SAT, which is on a 580 with a 70. And we want the distribution using a 0.1. All right. So if I go to StatKey and I plug in some values. So first of all, I do a little bit of converting, if you will. So this 25th percentile means 25% below some number. So actually, let's go to StatKey real fast and let's look at that. Let's look at the 25th percentile of a 580 and a 70. So I'm just going to read the data that I have over here. 25th percentile, 580, 70. I'm going to go there. I'm going to grab StatKey. I'm going to go to my normal distribution. I'm going to edit my parameters. My parameters were a 580 and a 70. So we're back at that 580, 70 thing again. Okay. I want the area to the left-hand side. And I wanted it to be the 25th percentile, meaning 25% of the data points are underneath of me. Well, that's 0.25. If I calculate that value, I come up with a 532.786. Okay, so I can find that score that's associated with that 25th percentile pretty quickly. 432 point, we could call it 432.8. I'm going to continue from where I was. Now, if I know that score is a 432.8, well, then I can convert that score onto a 0.1. Let me back up, sorry. I'm going to have to take one break for 1 second, and I'll be right back with you. Sorry I had to take a break there for a moment, but I had 2 very large peacocks trying to land on my roof of my house, and I had to take a moment to watch that. All right, so what did I do here? So I loaded the value of the score. I found the endpoint right here on the endpoint value. And so now that I know that endpoint value, I can do a little calculating here, finding a z-score. So to find the z-score for the standard normal, I can take the score that I know, 532, let's use 0.8. I can subtract the mu, which is 580, the center, and I can divide it by the standard deviation, which is 70, and I will get approximately, depending on how close we go to this, I don't know. Let me punch the numbers into my calculator real fast. About negative 0.675. What does that mean to me? That means to me that if I now made a normal distribution curve, that approximately negative 0.675 and below would account for the 25th percentile. So less than 1 standard deviation to the left-hand side. That's really what we're talking about here. When we're switching something, we're trying to say, hey, is it within 1 standard deviation, 2 standard deviations? How many standard deviations is it within? And that's really the goal in what we're discussing right now. So let's talk about using a graphing calculator in order to do some of this. Since let's get away from StatKey, if you will, a little bit. So it says to find the area of with a normal distribution of 0, 1. It's called the normal CDF, okay? And the command is, the normal CDF is the command. I'll show you how to get there in a second. And we're going to have to give it the lower and the upper numbers that we're calculating, okay? And it says compute the area of a standard normal distribution below a 1.03. So I want to be below a 1.03. So here's a 1.03 approximately, and I want the area to the left of that. And I'm computing what that would actually be. So I'm looking for the p-value because it says area. So I know I'm looking for the p-value. Okay, but we're not going to use our, we're not going to use StatKey. We're going to use our calculator. So I'm going to go to my calculator. A lot of escaping for me around here, just to let you know. So here's my calculator. And first of all, we're going to go where it says to go. And in order to calculate area, it's always the function normal CDF. Okay, so remember the StatKey has a bunch of cool stuff in it, and second StatKey has a bunch of cool stuff in it, and vars has a bunch of stuff in it. So I'm in the vars right now. So I'll do that for you again. The vars button, but the distribution is blue. So we go to second vars. And you can see that I have several different ones. And number 2 is the one we want to have right now, normal CDF. Normal CDF, number 2. So newer calculators are a little more advanced than the directions that we paste on the screen. The screens are for the basic calculator that doesn't really have anything additional. So let's talk about these numbers. First of all, the lower number, the bottom number. The bottom number is the number furthest to the left-hand side. Okay, well, on that curve that I had, remember, I was going way, 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 way far to the left. -1 E99. That's an incredibly small number. It's a -1 times 10, 99 times. It's like you're approaching negative infinity, if you will. When we use a lower number that tails to the left, we will always use -1 E99. My upper number. All right, well, I was calculating an upper number of -1.03. So I want to have a -1.03. That's where I want my area to stop. And I'll draw this in when we go back in a second. My mu value, I want it to be on a standard normal 0. And I want it to be on a 1 for the standard distribution. We're calculating area here, okay? Go down, I hit the paste button. Now, if you have an older calculator that doesn't give that little menu that I just had, you have to type in these numbers into the normal CDF function. It will open normal CDF, a parenthesis. You type -1 E99, comma, -1.03, comma. So it's always minimum or left bound, right bound, comma. I always put a 0 in because that's my middle. If it's not my 0 of middle, I'll change it to something else, comma, my standard deviation. And I'll write that out for you in a second. Hit enter, and approximately 0.152. So my area is about 15.2% or 0.151, actually 152. And I think that's what it actually asked me for. So when I go back here and I go from the current slide, I'm going to write in all the values that we just took care of right there. So first of all, when I did this, I did normal CDF, open my parenthesis, I did a -1 E99. That stands for this number way over here. Very, very infinitely far to the left-hand side, like negative infinity kind of stuff. Way, way, way far. Comma, my upper boundary, which was -1.03. Why did I use that? Because that was the statistic that I was asked to use, and that number is approximately right here. So what I've done is I've created an area in my calculator way, way far out here into a negative infinity world. I'm getting all the numbers to the left. Comma, the last number is going to be my mu, which was my center, and then my standard deviation 1. So you always have it in this particular thing. So I'm going to add to your command up here. It's the lower, comma, the upper, comma, the mu. Oof, sorry about that. Let me get an eraser going here. Got a little crazy there, and I have to go back to it. Upper, comma, mu, comma, sigma. That's how you always want to enter your command for your normal CDF. So we have found that we had approximately that 0.152 p-value. That's what we were searching for. It says, compute the area above a 35 on a normal distribution with a mu of these values. So what I'm going to do is I'm going to pause. I'm going to give you a couple seconds to work, and we are going to come back, okay? Okay. Hopefully you've got your commands done and those things, and we'll calculate what I have here. So in this one right here, I'm doing a normal CDF. It says the area between area above 35. So I'm looking above a 35. So first of all, I have a middle, and that middle is a 50. And it's counting by 7. I want above a 35, which is about here. So I want a lot of this. So my function would be my normal CDF. My entry would be 35, lower, upper. Now I'm going to use +1 E99 because I want that number to go really, really far to the right-hand side instead of the left-hand side. I'm going to go with a comma 50 because that's my middle, and I'm going to count standard deviations by 7, and I'm going to get approximately 0.984. That's about 98.4% area underneath of that curve. For the next one, I can see that right away I've got a 55 and an 80, so I'm stuck between two numbers here, computing area 55 to 80. In that 55 to 80, I have a middle of 50 and a center of 7. So my middle is 55, and I'm finding somewhere between a 55 and an 80. Okay, well, a 55 is above a 50 at the middle, right? So remember, this is my mu. This is my standard deviation. So I've got values which are between here and, I don't know, 80, which is out here somewhere. I'm trying to find p-value over there on that right-hand side. So my normal CDF is going to be 55, comma, 80, comma, 50 on a 7, just as typed out, and approximately 0.238. Pretty straightforward on the calculator. Let's say that we're going to switch out of area. Now we're going to go find an endpoint or a z number. We're on a 0, 1, so we know it's a z on a 0, 1. So now we're going to use a function which is inverse norm. It's going to be a different function, but it's very similar to the same. It says the command for the inverse norm is the area to the left. Now, some calculators will do area right and area left and area center, but I'm going to summarize on area left first, and then I'll look at the other two options that are available. It says it's not necessary to enter the mu and the standard deviation on a 0, 1 because it's always there. I always put it in just because I don't trust my calculator, but it is supposed to always be a 0 and a 1 if you don't enter them. It says find the endpoints on a standard normal distribution if the area below z is 2.5%. Okay, so we're looking for some z number. We don't know what it is. We want the area below it to be approximately 2.5%. Yeah, 2.5%, which is 0.025 as a decimal. Okay, that's important that this number is this number because we can't put in 2.5% to our calculator. So I'm going to switch out. I'm going to go to my calculator so you can see it. So now when I go to vars second, now I'm going to go down to number 3, which is inverse norm. Okay, number 3. So now it says, okay, what do you want the area to be? I want the area to be 0.025 because that's what it said. If I don't enter these numbers, they're automatically 0 and 1. And newer calculator is going to ask you left, center, right. If it doesn't ask you this question, it's always left. I'm going to hit enter. And come on, I got to scoot down. And I'm going to paste this thing. This is the command line you see right here. So if you don't have a calculator that shows you the menu that I'm showing you, then it'll say first number is your area. Second number is your mu, and the third number is your standard deviation. And I've told it I want to be on the left side. Okay. These things don't need to be inserted because they're always guaranteed to be 0 and 1 per the calculator. And you're just telling it I want the area to the left of a 0.25. If I hit the buttons, approximately that number that I'm looking for is 0.196 in a negative. 0.196. So that is my z-score that I'm looking for. Oops. That's my z-score that I'm looking for on that area. So we'll draw that in and make sure it looks all pretty and nice. So we know that about 0.196 negative is my value. And that 0.196 will give me an area of approximately 2.5%. So I have found an endpoint based on given an area. Find the endpoint on the standard normal. Distribution for the area to the right of a z that is 8%. Okay, so first thing, I'm going to use an inverse norm, right? And I'm talking about now, if I'm going to talk left area, like most people have, then I'm going to calculate always in left area. So if the number I'm talking about, okay, so if this is 8% here, so I'm looking for some number right of z that's only worth 8%. Well, that means that the stuff over here on the other side is worth 92%. So if we're talking left area only, then my calculation is going to be based on 92% instead of 8% because my calculator likes left area. So I'm going to use an inverse norm. Because remember, an inverse norm is the one that will use area to find an endpoint. I'm going to put in 0.92. I know that it's always going to calculate a 0 and a 1, so it's just an inverse norm of 0.92, and it's going to equal a 1.41. Now, you can try that if you have a calculator that calculates right area and do area to the right at 8%, 0.08, and you can do that calculation, you will still get 0.141. Find the endpoint. So now we're doing an endpoint, right? And the endpoint on a standard normal. So again, 0, 1. If the area is between z positive and z negative, is between z and z negative is 68%. Okay, so what does that look like? Okay, well, that looks like some number here and some number here, and it's got 68% sitting in the center. Well, that means there's 32% not accounted for, so that means there's 16% here, and there's 16% here, and it's symmetric. That's a key word here, symmetric. I keep getting these lines. I'm not quite sure why I'm getting those lines today. So what I'm going to do is I'm going to focus on this z-score right here. Because if I can figure out that z-score, then I'll know the other z-score also because of symmetry. So what I'm going to do is I'm going to look at my calculator and I'm going to say, hey, I need to calculate the z-score for that bottom end number. Okay, so I'm going to use inverse norm. That inverse norm calculation is going to be based on 16%, 0.16. And if I want to go ahead and put the 0 and the 1 in there, I can, but I don't need to. And when I do that, I'm going to get a return of negative 0.994. Remember, this is not area. This is a z-score. This is the z number on the left-hand side. I've just found it. Okay, well, what's the z number on the right-hand side? Well, it's exactly the same thing, but it's the positive version. Because symmetry takes place, and we have to have two numbers, the z's are plus and the z's are minus. Those two z-scores will be identical. And again, I calculated the area to the left because my calculator finds the area to the left. Once I knew the area to the left, I knew it would be repeated on the right-hand side with the same positive z-score. It says finding the endpoint or z with a normal distribution. And it gives you the nice steps. It shows you the steps at the top of the page, and you really can't miss these steps. So when we look at this value, and now this is a normal, not a standard normal. So now we're going to have a middle that's not a 0 and not a 1. So we have to enter those data points. And you can see that it tells you inverse norm, area to the left, comma, mu, comma, standard deviation, hit enter. So it says find the endpoint on a normal distribution with a mu of 50, standard deviation of 7, if the area to the right is 90%. Okay, now they're trying to mess with us because they're giving us an area to the right of z at 90%. Okay, well, 90% is a lot, right? So if this is my z number we're looking for, right, and this is worth 90%, then the area to the left is worth 10%. So I'm going to do my calculation based on 10%. I'm going to take an inverse norm. That's what the formula says, or the command says. I'm going to tell it, hey, give me 10%. But I want that 10% based on a 50 distribution and a 7. That's my distribution. We're not finding a z-score here. We're finding an endpoint, okay? We could convert this endpoint to a z-score later, but right now we just actually need the number. Hit the buttons. 41.029. This is my endpoint, which will split the data 10% on the left and 90% on the right. Practice your calculator, practice finding inverse norm, practice finding endpoints. You can also do some Google searching too. Let's summarize. The density curve shows the proportion of population as an area under the density. Standard normal is always on a 0, 1. Technology is StatKey, but I would rely more heavily on graphing calculators, folks. They're much more useful than the StatKey, but we do need to know how to use both. enjoy yourself. We have finished chapter 5, or 4, sorry, and we are on to chapter 5 next.